because that was a little bit easier of a section, or that piece of the section. It wasn't the full thing, but that was a pretty easy part for you to do without me. So we're going to go back and hit 6.1 now. So this is talking about inverses. You did do this in Algebra 2, so hopefully some of this sounds pretty familiar to you. First thing I have on here is just a definition. We're talking about one-to-one functions. So a one-to-one function is one where two different inputs in the domain correspond to two different outputs in the range. Okay? In other words, if it is one-to-one, every x value gives you a different y. Or you could say, if it's one-to-one, y never repeats. We know if it's a function that x doesn't repeat. If it is one-to-one, y doesn't repeat. So we're just going to look at some different ways that functions might be represented and decide if they're one-to-one. We'll start off simple. If we look at just a mapping, would this mapping be one-to-one? Why?
Because the 61 and the 55 repeat with the same 30.
Yes. So this is not one-to-one. I usually just do 1-1 for one-to-one. The reason being is that 38 repeats. What about B? Is that one-to-one?
Yes.
Yes, if you look, your y values are all different. So yes, this one is one-to-one. Now, if our function isn't listed out as ordered pairs or a mapping function, then we need other ways to figure out if it's one-to-one. So we're going to talk about a couple. We're going to look at an algebraic way and then a graphing way. Algebraically, if it's one-to-one, you can't get the same y value twice. So what we are going to do to prove it's one-to-one algebraically is we're going to plug in two different x's. We're going to put in an a and a b for our x, and we're going to set those equal to each other. When we do that, the only way we can get the same y value from there, if it's one-to-one, is if we have the same x to begin with. So we are going to do f of a equals f of b and solve. If you get a equals b, that means it is one-to-one. The only way the y's were equal is if the x's were equal. If we get anything else, then we'll say it's not one-to-one. So let me explain that through an example. I'm trying to decide if this is one-to-one. So what we're going to do is pretend we do get the same y value twice. So I'm going to put in an a and put in a b and set those equals. So we're going to do f of a equals f of b. So if you put in an a, you get negative 3a plus 7 equals, if you put in a b, you get negative 3b plus 7. Now we solve for a. So to get a by itself, what would you do? Subtract our 7, which would cancel it on both sides. And then so those would cancel, and I get a equals b. So I pretended I got two different y's, and what happened is my x's have to be the same. So if you get a equals b at the end, that means, yes, it is one-to-one. Let's do another. So, to decide if it's one-to-one, we do f of a equals f of b. f of a would be square root of 49 minus a squared. F of b is the square root of 49 minus b. If I'm going to solve for a, what would we do? Square each side. So we have 49 minus a squared equals 49 minus b squared. Then what do? Subtract our 49. Divide by -1. To get a by itself, now I square root. When you add a square root, what do you have to put with it? So the square root of a squared is a equals plus or minus square root of b squared is b. So what I have found is I can get the same y value out if I put in the same numbers, or if I put in a positive and a negative. In other words, positive 7 and negative 7 give me the same y value out. So what does that mean? If you get exactly a equals b, it is 1 to 1. If you get anything else, it's a no. So this, we had two options. They could have been the same or they could have been opposites. So that means it is not 1 to 1. Things that are going to make it not 1 to 1, watch for those squares. That's usually a pretty good indicator, because to get rid of the square, when you do your square root, you have to do plus and minus. So a lot of times that will be something that will make it not 1 to 1. Now, we can work this out algebraically, but it would be nice to have an option that didn't require all of this work. And so we can also look at a graph. If you think about it, if something is a function, that means that your x's don't repeat. And so when we looked at a graph, how did we tell if our x's repeated? Vertical line test. If it is 1 to 1, our y's can't repeat. So we could look at the horizontal line test. So if every horizontal line hits it in at most one point, it's 1 to 1. If you can draw any horizontal line that hits it more than once, it would not be 1 to 1. So let's use a graph to decide some of these. Obviously, we have a graphing calculator, but we don't need it here. What's x squared look like? Quadratic. You can draw lots of horizontal lines there that hit this thing more than once. So this one is not 1 to 1. What's x cubed look like? Can you draw any horizontal line that hits that more than once? No. No matter where I put it, it only hits my graph one time. So that one is 1 to 1. So unless I specifically say you have to do it one way or the other, you could use either of those options. You can either work it out algebraically. Most people tend to prefer graphing and looking at the graph and checking for the horizontal line test. So it won't matter to me as long as you can do both ways. Any questions there? So we've been talking about these 1 to 1 functions because if a function is 1 to 1, it has what is called an inverse. To find the inverse, we switch the x and y values. A lot of times you will see this f to the -1 power, that is the symbol for inverse. It does not mean 1 over, it means we have reversed the x and y. So let's just look at a set of ordered pairs and find the inverse first to kind of illustrate what we mean. If I wanted the inverse of this, first of all, is it 1 to 1? Yeah, I know. I don't have any of the same y values, so that's okay. What would happen if it wasn't 1 to 1? Yeah, when you flipped them, your x's would repeat, and then it wouldn't be a function. So that's why we want 1 to 1 to begin with. So the inverse here would be what order pairs? find the inverse, I said you just reverse x and y. So if it was negative 327, when I reverse that, it becomes 27, negative 3. You just flip them. So negative 2, negative 8 becomes negative 8, negative 2. Negative 1 will stay the same. 0, 0 stays the same. 1, 1 stays the same. And 2, 8 would become 8, 2. So all the inverse does is flip the x and y. So what's happening is the domain in the original, the x's in the original become what in the inverse? The y's, they become the range. So the domain of the original is the range in your inverse. The range in the original becomes the domain in your inverse because we just flip the roles of those x's and y's. Another property of inverses, they are opposites of one another. So if you compose them, if you do both operations, you should get back what you started. Okay, so let's think in terms of something simple. If I am adding 2 to a number, what would be the inverse of adding 2? The opposite of adding 2? Subtracting 2. So if I start with a 5, and I first add 2 and then subtract 2, what do I get out? I get 5. If I start with a 5 and first I subtract my 2 and then I add my 2, I'd still end with a 5. So if they are inverses, you should be able to compose them, and you should get x out both times. So we're going to use that property to check if some functions are inverses of one another. So if I want to know if these are inverses, it is not enough to show one way. You will have to do both. So we're going to have to do f composed with g and g composed with f. If they are inverses, the answer to both of those problems should be x. If even one of them is not x, then I can automatically stop and say they aren't inverses. So f composed with g means f of, if I plug a g in there, that's 1/2 times x plus 3. Do you guys remember composing these? It's been a little bit, but we did it. So now you're going to plug that into f. So you go to function f, which is 2 times, and for your x, you are plugging in that inside part. 1/2 times x plus 3. And we have the plus 3 on the end. So you're just taking the entire function g and plugging it in for the x in f. Now we simplify. What's 2 times 1/2? 1, so those cancel, so I get x plus 3 plus 3, so that's x plus 6. What does that tell me? It's not. I didn't get x back. There is no need to check the other one. I know right now these aren't inverses because I didn't just get x out. Try a few more of those. So if I do f composed with g, g is 1/x plus 1. If I put that into f, f is 1 over whatever you plug in, minus 1. Okay, so if I start simplifying this, what happens on the bottom? Plus 1 minus 1. Those just cancel. To divide fractions, we flip and multiply. So 1 times x over 1 is x. Is that enough to guarantee these are inverses? No, you have to check both. Yes, ma'am.
Okay, so when you're plugging in, I always have trouble, so f of g of x.
You start inside. So you're going to take G and put it into F. So we have to do G of F now. So we start on the inside. Start with F. And we are going to take that and put it into G. Replace the X in G. So that's 1 over x minus 1 plus 1. So I have a fraction divided by a fraction, which means flip and multiply. What happens with 1 times x minus 1 over 1? And we just get the x minus 1 plus 1, which is x. So those are inverses because both ways it turned out to be x. One more. So if I do f composed with g, I'm going to take my entire function g and plug it in for the x in my f equation. So you have 3 times the negative 1/3 x minus 4 with a plus 4. 3 times negative 1/3 would be negative 1. If I distribute that, I get negative x plus 4 plus 4. So negative x plus 8. So what does that mean? They're not. We don't have to do any more. If one works, you have to make sure they both work. But if one doesn't, you get stuck. Any questions about that?
Could you distribute them to the
Sure. And then multiply your 3. Absolutely. Alright. In terms of our graph, when you find an inverse, you just switch your x and y. So the graph of a function and the inverse are symmetric with respect to the line y equals x. In Algebra 2, when you graph functions and inverses, you always graphed y equals x and made sure it was symmetric across that line. So I just want to illustrate this with a couple graphing problems. If I want to graph the inverse of this line, let's start by graphing that line. We know if we're graphing a line, we start at our y-intercept, which would be negative 2. Slope is 3, so up 3 over 1. And I'm not going to draw a straight line, so I'm going to put several dots here. Okay, so this is, that is crooked, my original. So if I wanted to graph the inverse, all you have to do is flip your order pairs. So for instance, this had the point 0, negative 2. So the inverse would have negative 2, 0. This had the point 1, 1. So your inverse would still have 1, 1. That's enough points for a graph, but I'll do a couple more. We had 2, 4. So that would become 4, 2. if you drew the line y equals x, that's just the line y-intercept is 0, slope 1. So it has points like 0, 0, 1, 1, 2, 2, 3, 3, 4, 4, and so on. Do you see that if I folded my graph on that green line, the red and blue would overlap one another? Yeah.
Okay, so like so I feel like the opposite of 1 would be negative 1, but it's just...
You're not even doing the opposite, you're just flipping the ordered pair. So, if,
Okay.
so like at the point where 1, 2, you're just going to 2, 1. So don't change the sign, just change the order. Other questions? Another one? On this one I gave you the graph to start with and just asked me for the inverse, so all we need to do is find some points on it. We have a point 1, 2, so that would go to 2, 1. We have 0, 1, so that would become 1, 0. Negative 1, 0, be 0, negative 1. Negative 2, would that change? No. So if I could draw straight, we get something like this. You could see the line y equals x would go right through the middle of this. And so they are symmetric across that. I know I'm teaching for pretty much the whole class today, but I want to go ahead and talk about how to find an inverse, if you guys can stick with me just a little bit longer. You did this in Algebra 2 as well. In finding an inverse, we always first rewrote the equation. If it started with an f of x, we would change that to a y. Then you get to switch your x and y, solve for y, and then at the end we would go back to function notation and change our y to f inverse. So those are the steps for finding the inverse. The only new piece that we're doing this year is we're going to do domains and ranges of them sometimes. That's really the only thing that you didn't do in Algebra 2. So if I want to find the inverse of this, first step, instead of f of x, we are going to write y. Second step, in an inverse, x and y flip roles. So this becomes x equals 2y plus 3. Now we're just going to get the y by itself. So if I subtract my 3, divide by 2. And final step, I do want it to go back to function notation. So instead of y, we are going to write f inverse, so that f to the negative 1 of x equals x minus 3 over 2. I asked for a domain and range of the function and the inverse. So what I usually do is I list them and I put a subscript, D for domain and then either an f or f inverse so I know which one it is. Domain of the original. If you look at the original, the only thing that you really have to worry about if you're finding the domain, if it's a fraction, we know the bottom can't be 0. And if it's a square root, we know it has to be positive inside. Do you have a fraction or a square root? So what would my domain be? Negative infinity to positive infinity. And we know the domain of the function becomes what? The range and the inverse. So as soon as you know the domain of the original, you also know the range and the inverse. Without a graph, it's a little harder to look at ranges. So let's jump down and look at the domain of my inverse. my inverse had a fraction. What would make the bottom 0? Would anything make 2 equal 0? So what's the domain of my inverse? And that is the same as the range in your original function. So this one, it was just a line anyway, so not very interesting. Everything was negative infinity to positive infinity.
Will it always be like that, no matter what?
That they're all infinities, or?
No, where the domain of the
Yes.
first one would be the range of the second.
Yes, always. Let's do one more. So first step is what? Change f of x to a y. And then we have to switch x and y. So y becomes x, and every single x you have would become a y. Okay, we have to solve for y here. So first let's get rid of the fraction. I'm going to multiply my y minus 1 to each side. So that would give me an xy minus x equals a 2y plus 1. We have our y's in 2 spots, so I need everything with a y on one side and everything without it on the other. So I'm going to subtract this 2y, and I'm going to add over my x. xy minus 2y, they're not like terms, so I can't actually subtract them, but what could I do? Take out that y. Then to get y by itself, we would divide. It's multiplied, so we divide. And final step, instead of y, we write f inverse. Let's do domain arranges. Domain of f. If I look at the original, it is a fraction. What's the one thing x can't be? 1. So my domain of f would be negative infinity to 1, union 1 to infinity. And that is the range in my inverse. Okay, let's look at the inverse. X can't be 2. So the domain of the inverse is negative infinity to 2, union 2 to infinity, which is the exact same thing as the range in the original. If you had a square root. All right. There are 4 examples left. We have covered all of the material at this point. The examples, I have a couple more inverses and then just a couple that we have to think through. So we will talk about the last ones tomorrow. The homework for this section is Math Excel. It is a longer assignment. It's like 30 questions, but a lot of the questions at the beginning are fill in the blank. And if you have your notes handout, you'll be able to get those pretty quickly. You know, it'll say a function, if a function is 1 to 1, then it has a blank, it has an inverse. So they're going to go pretty quickly for a while. Tomorrow, after I finish my last few examples, you will have time to work for the rest of the class period. So the Math Excel will actually be due on Wednesday. So tomorrow we'll just finish up the notes and then have class time, but you might want to get a jump start and do at least a little bit of that before tomorrow.